So welcome everybody. Thanks so much for showing up. It's my pleasure to welcome Hal Dalmay here to Microsoft Research. Hal and I have known one another for like 20 years maybe, or if not quite, almost that. But most recently he's an associate professor at associate professor. I was trying to promote you, Hal, at University of Maryland, and his schedule is mostly full today, but I think there's a half-hour slot free. So, so let me know afterwards if you'd like to meet with him. And thanks, Hal. Please take it away.
Yeah. Okay. So thanks for coming. Thanks for coming. Sorry, I'm a little tired this morning for some reason. Okay. So. I'm going to talk about learning language through interaction. So before I get started, I'm going to try to sort of like motivate and give a sense of what I'm going to talk about. So we've had a lot of success over the past like 20 years doing like machine learning for NLP. And the like dominant paradigm there is you basically collect a bunch of labeled data, you train a system, and then it works really well. But it works really well like only for like the narrow task and the narrow domain and the language that you've picked. And pretty much doesn't generalize to anything else. And I guess my view is that it's unlikely that we're ever going to have sufficient labeled data for every task, for every domain, for every language that we could possibly care about. And so I think we need some alternative form of supervision that we can learn from. And so the like sort of big picture message that I'm going to try to like convey today is that like one thing we can do is build some system somehow. It could be a statistical system, it could be a rule-based system, it could be, you know, whatever you want, and then actually deploy this system in some sort of like real-world setting where it's interacting with people, and then collect feedback from those people and use this to improve the system over time, and essentially use this to drive the learning. So that's sort of the goal. I'm going to talk about this in like an NLP context. So this is my like standard what is NLP slide. I'm going to focus sort of mostly on what's categorized here as like complex language problems. So these are things like speech recognition, translation, information extraction, dialogue, question answering. There's of course like this general like what does it mean to understand language? I have no idea what that means, so I'm not going to work on it. In particular, I'm going to talk mostly about machine translation and question answering today. And so I guess one other like minor comment. So I do believe in learning through interaction, so you should ask questions. There's plenty of stuff that I can compress if we go slightly behind on time. All right, so I'm going to start with this project we've been working on for maybe like 4 years now. So this is stuff that I've been doing mostly with Jordan Boyd Graber, who's now at UC Boulder. So if you've heard him give a talk, you can leave now and I won't be offended. I'll talk about some like different angles than maybe you might have heard him talk about. So I'm going to talk about this simultaneous translation project. So so has anyone actually seen a human simultaneous translator work? Oh, actually quite a few people. It's super amazing, right? So like they're listening in like one language and they're speaking in another language and like somehow their brain does this translation. I don't know how it happens. I mean, the people that I've talked to, it's almost this like semi-subconscious thing where they don't necessarily even have like strong recollection of what it was that they said. But somehow like this like system pipes through their ear and out their mouth and it works. So this started basically at the Nuremberg trials at the end of World War II, and this was because there were a bunch of defendants and they did some like back of the envelope calculation, and if they had done consecutive translation, which up until that point had been the standard, like someone says a sentence, then it gets translated, and then they say another sentence, the trials would have gone on like forever. And so they invented simultaneous translation or simultaneous interpretation as a way of solving this. And so one of the key aspects is that if there's a long delay between when something's said in the foreign language and then translated into the English, or not necessarily into English, into the target language, this can lead to bad conversation. So in the simultaneous interpretation literature, this is either called like ear-voice span, so how long from your ear to your voice, or also décalage. So this is a little bit embarrassing, but I'm going to give a Skype translate demo because to sort of motivate a couple of things. So probably you all know what Skype Translate is, I would hope. And probably most of you have actually seen the video that I'm about to show, but I'm going to show it anyway.
Good afternoon, Melanie. How are you?
Aber nach neuen Melanie, wie geht es dir?
Mir geht es gut. Wie geht es dir?
Well, how is it, me friends?
Sorry, Melanie, say that again.
Melanie, sag das nochmal.
Mir geht es gut. Wie geht es
I
dir?
am well. How are you doing?
Okay, so why did I show this? So I showed it for a couple of reasons. So the first is okay, so this is like super awesome and amazing and impressive. But and I'm not just saying that because I'm here. Like, I really do believe that that's true. But it's also like, I would get super frustrated having a consecutively translated conversation with someone, right? So I think that dialogue is really the case where you really do want simultaneous interpretation and you really do want as little delay as possible. Because unless it's a high stakes environment, like I'm in a courtroom or I'm talking to a doctor where I'm willing to wait the extra time, like if I'm talking to, I don't know, a friend on this, or a friend of a friend on the street who doesn't speak English, I'm probably gonna give up pretty soon if there's like such a large delay. So that's one thing. The second thing is this like, sorry, Melanie, say that again business, right? So this is like a pretty clear signal that whatever the system had just done was probably wrong. And you would want to learn from that, right? So you don't know what the right answer would have been, but you at least know that whatever it was that I produced was not the right thing to produce. So then the other thing that's interesting is after, I don't actually know what that guy's name is, but does anyone know? No? Okay, that's fine. After he says, sorry, Melanie, say that again, she then repeats herself, and it gets translated properly as whatever. I am well, how are you, or something. Which again provides some sort of like implicit feedback about what the system maybe should have done the first time around. So I'm going to talk about two types of feedback, and it's probably worth differentiating them. So one that I'm going to call explicit feedback, and the other that I'm going to call implicit feedback. So to me, sorry, Melanie, say that again, is implicit feedback. Now, you might say, well, it's actually pretty explicit that the system did something wrong. But to me, explicit feedback means like some numerical score that I'm going to try to optimize. So like a thumbs up, thumbs down, or like a 1 star to 5 star, or something like that. So this is not a 1 star to 5 star. You could imagine a system that converts, say that, Melanie, say that, sorry, Melanie, say that again, into an explicit rating. But I'm going to talk mostly about implicit, meaning like sentences like this, versus explicit, meaning some numerical score that I want to optimize. And so for most of this talk, I'm going to talk about explicit feedback, and then at the end, I'll say a little bit more about implicit feedback. Okay, so that's the setup. So I want to say a little bit about why simultaneous interpretation is hard. So it's hard because languages are different, and they're not just different in that they use different words, but they also put them in different orders. And this can cause problems. So I have an example here from glossed Japanese. So if I want to say the dinosaur went to the store, I'm going to say something like dinosaur store go. So Japanese puts verbs at the end, whereas English puts verbs in the middle. This has correlations with other word order effects. So like relative clause position with respect to the noun it modifies is strongly correlated with verb object position. So in Japanese, relative clauses go before the noun that they modify and the verb comes at the end. So if you want to say the dinosaur who wanted to buy food went to the store, you say food by dinosaur store go. So the problem here is that if you're translating from a verb final language to a verb medial language, you often run into this case where you need to produce the verb on the target side before you've heard it on the source side, and then this basically forces you to delay for a while you're waiting for the speaker to say whatever the verb is going to be. So in case you don't think that this is actually a problem, like languages in the world are about 50-50 split between verb object and object verb. So English is here. These are Native American languages. So English is a red dot because it's verb object. Japanese is a blue dot because it's object verb, and it's basically half-half. So if you pick two languages at random, chances, 50% of the time, you're going to have to deal with this problem. Okay, maybe if there's probably a non-uniform distribution over languages you actually care about, but if you cared uniformly about all languages in the world, that would be your problem. Okay, so I'm going to say like one word about how, or one slide about how normal statistical machine translation works, just so we're all on the same page. So we collect a bunch of text that's been translated offline by people. So the Canadian Hansard is the classic example of French-English data. We break it into aligned sentence pairs between the French and the English. We learn some sort of statistical model to map from one to the other. And then when we get a new test sentence that we're trying to translate, we somehow apply this statistical model to get a translation of that sentence. Okay, so that's machine translation in like 22 seconds. I'm going to say nothing else about how sort of normal machine translation works. For the results that I'll show in this talk, some of the earlier ones will be phrase-based machine translation systems. Some of the later ones will be neural machine translation systems. But it doesn't really matter. We're going to use an off-the-shelf machine translation system as a black box and then try to make it more simultaneous. Okay, so one of the things that we were interested in is like, how do simultaneous interpretations differ from what I'll call batch translation? So when you give a translator a sentence and just have them translate it. So what we did was we took a bunch of Japanese TED Talks and we had a human interpreter interpret them into English live. And then afterwards, we gave a transcript of the Japanese to a translator and had the translator translate it with essentially infinite time. So here's a Japanese sentence. So who speaks Japanese? Okay, so I can't lie about what it says. Okay, so we have a Japanese sentence. The batch translator produced, they might recognize expression 1, but not expression 2 to 4. It's a pretty reasonable translation. The interpreter said the phrase number 1 only is accepted and phrases 2, 3, 4 were not accepted. And so this is a case where the verb recognize comes later on the Japanese side. And so the batch translator is able to like move it earlier to produce a more natural English sentence. But the interpreter has to wait a while and say a bunch of other stuff before they hear the word, they hear the word recognize and translate as accepted. Okay, so that's one example. So we did a sort of a corpus study of this data and lumped different types of differences between batch and interpreted text into a couple of categories. So the biggest are these word ordering categories. So there are basically two common types of inversion. So one is you segment a single Japanese sentence into multiple English sentences, because this gives you some flexibility about where verbs go. And sort of the obvious thing is passivization. So if you're in English and you want to move a verb around, the easiest way to move a verb around is to passivize the sentence. So these are both quite common. There's a lot of word generalizations. So human interpreters are working under like this massive time pressure. Your retrieval of words is fast for frequent words and slow for rare words. And so interpreters will often use like hypernyms because they're faster to think of, right? So like, I don't know, if I'm trying to translate into like Japanese and someone says sea bass, it's gonna like take me, okay, well, I like sushi, so I probably actually will remember how to say sea bass. But in general, like I might not remember how to say that specific thing, and so I'm just gonna say fish because probably it doesn't matter unless we're having like some conversation about like sea bass fisheries, in which case probably I've studied ahead of time and I know how to say sea bass. So word generalization also interacts with inversion. So one of the things that interpreters will do a lot is they'll try to guess what the final verb is going to be, and then just like cross their fingers that they're right. But in order to like hedge their bets, they'll often guess a more general verb than the one that they'll actually see. So someone in Japanese might say something like, yesterday I to Tokyo flew. And an interpreter might say like, yesterday I went, because they haven't heard flew yet, but maybe because of context they guess went. So they'll say, yes, sir, I went to Tokyo, and then they'll hear flew, and they'll say like by plane or something like that. So you get this generalization and then a repair later. So this is a pretty common strategy. And then finally, you get summarization and omission. So this is basically to catch up. So they just drop content because they're behind or because they've forgotten or whatever. So here are a couple of examples. So we have a Japanese sentence. The batch translator produced one of the characteristics of honorific Japanese is that cannot be adequately expressed when using a direct translation from English to Japanese. The interpreter does segmentation. So they say, now let me talk about the characteristic of the Japanese polite expressions. And such expressions cannot be expressed enough by just translating directly. So there's a segmentation here, and then there are also two generalizations. So instead of saying honorific, they say polite. And instead of saying adequately, they say enough. So here's another example. So its third characteristic is that its output is as much as possible in the natural language of spoken Japanese. And then the interpreter, instead of saying characteristic, says feature. Instead of saying as much as possible, says very, because they're like running behind at this point. And then they completely drop saying Japanese, which actually does appear in the Japanese. It's not like the batch translator is just making it up. I mean, that happens too. But in this case, the interpreter just dropped it. Okay, so these are the sorts of things that these are the sorts of strategies that we'd like to learn in order to have a model that can be more simultaneous with the input speech. So basically, we're going to try to learn a model that makes sort of these interpretation style decisions as we go along and like calls out to a black box machine translation system to do the actual job of the translation. Okay, so how is this going to work? So, oh yeah, question.
So the existing parallel corpuses are all batch translated, or do you have some?
We have some interpreted data. It's much smaller. So there are a handful of corpora that are out there. So there's a UN corpus that's Spanish, Italian, English that's reasonably big. There's Japanese English, like TED Talks. There's a Chinese English corpus, which I was going to get, and then the guy who made it stopped responding to my emails. So the thing that's interesting is most of these corpora were actually produced by people who do like corpus linguistics and study simultaneous interpretation as like, most of them are not created by computer scientists. In particular, the Chinese one was like that. So there are data sets, they tend to be much, much smaller, and there are far fewer of them. But we'll use them.
So as a follow-up question, do you think, are there any things that the batch translators are doing that you sort of want to unlearn, that they're like putting in extra effort that's unnecessary, that, you know, I don't know what that would be, but.
Well, I mean, one of the things that they do that we don't want to do is they reorder stuff a lot. But other than that, I mean, I'll say a little bit more about this later, but one of the things that's really interesting here is that the batch translators are really good at getting the meaning across and being fluent. The interpreters, I mean, these are not like super fluent, and they're not like super adequate either. I mean, they're good. This interpreter is actually a very good interpreter. But they're definitely not perfect. And somehow we want like a best of both worlds, where we get the simultaneity that the interpreters have, but we also get like the high quality fluency and adequacy that the batch translators have. So we haven't totally solved that, but I think that's one of the interesting questions. Okay, so, right, so we have this model. So at every point in time, the model has a couple decisions it can make. So it can either wait, which means listen for another word. Oh, and so full disclosure, we're not doing speech recognition. So we are working off of transcripts, and the transcripts are perfect transcripts. So take that for what it's worth. So you can wait to hear another word. You can predict what you think the head verb of the current clause is going to be. So if you're in a relative clause, that means the verb in the relative clause. If you're in the main clause, that means the main verb of the sentence. You can also just try to guess what the next word is going to be to try to get ahead a little bit. Or you can commit, which basically means speak, where speak actually means write it down. We're not doing speech synthesis either. Okay, so we have some state. So this is the environment. So this is the words that we've heard so far on the Japanese side. And then we have internal predictions about what we think the next words are going to be. Yeah?
So do you have punctuations?
We do not have punctuation.
But you do have sentence boundaries?
We have utterance boundaries, which is not exactly the same. Which in this case basically means long pauses. Right, and then, like I said, we have example data from human interpreters where we can look at what the human interpreters did, right? So we can sort of reverse engineer, was the human interpreter waiting here? Did they make a prediction here, right? Are they saying a word that they haven't heard the source for? Are they saying a word, are they translating a word that they've already heard, and so on? So we can reverse engineer what the human interpreters are doing, yeah.
You have timestamps for each word within a
Yeah, so we have timestamps. I mean, it's not perfect. We have timestamps for the beginning of every word. I mean, we could, and then we do like forced alignment with the transcripts and stuff like that. Yeah, we couldn't do this without the timestamps. Okay, so how does this work? So here's a German example. I don't speak German, sorry. So it's like, ich bin mit dem Zug nach Ulm gefahren, which means I am with the train to Ulm traveled. So at some point in time, the system will have heard like mit dem Zug. It has some internal state. So it's predicting that the final verb is going to be gewesen, which I think means have. Does anyone speak German? What is it? Ben. Okay. Like I said, I don't speak German. This is wrong. It's predicting the next word is going to be und, which is also wrong, so hopefully the system learns to wait. So then here's a little bit more of the input. It thinks the final verb is going to be geliefert, or however you say that. So what does that mean?
Deliver.
To deliver, okay. Thank you. I should actually just like put this on the slide so that I know. Which is also wrong. It thinks the next word is going to be nur, which is wrong. So now it hears nach. It thinks the verb is going to be gefahren, which now is correct. It thinks the next word is going to be Berlin, which is actually a pretty reasonable guess, but in this case it's wrong. So what we want it to do at this point is we want it to predict the final verb. So now it has the words that it's actually heard plus its predicted final verb. We're going to shove this through our black box machine translation system, which is going to do something or other, whatever it does. And it's going to produce something like I traveled by train, which the system will now say. Okay, so now the system still thinks that the next word is going to be Berlin, so it's going to wait again. And now here's Ulm, so it can choose to translate that. So this is our commit, so we commit to the translation of to Ulm. And now we've heard the entire sentence and we can decide to stop. Okay, so that's basically how the process is going to work under the hood. So then the question is like, how do you train this thing? At least initially, we're going to train it using this algorithm called Dagger, which is like my favorite algorithm, which I will describe in one slide. So I'm going to like do mixed metaphor, and we're going to switch to driving a car rather than interpretation, but it's exactly the same. You're in some world and you're trying to choose actions. Okay, so how does the algorithm work? So we put an expert in the car, so the expert is going to be like the human interpreter. The expert's called Pi star, because that's like a good name for an expert. And so Pi star drives the car, and at every state visited by Pi star, we collect an example where the input is the state and the output is the action that Pi star chose at that state. So this gives us essentially a big labeled data set of state action pairs. And we can feed this into whatever off-the-shelf classifier we like, some neural network thing or logistic regression or whatever your favorite thing is. So this is going to give us a policy, Pi1, that hopefully will predict, or it will predict actions in states. Hopefully it predicts good actions. The problem is that Pi1 has only been trained on states visited by the expert, which means that if it ever gets like off the sort of gold standard trajectory, like life could go bad. So we want to let Pi1 learn to recover from its own errors. So the way we do this is we let Pi1 drive the car, but we put some poor expert in the car while Pi1 is driving, and the car completely ignores whatever the expert is saying, but records it for posterity, right? So The car is driving along and the expert is like madly trying to steer it back onto the road. The car ignores them, but it collects their actions as labels. So we get a bunch of states visited by the previous policy, and we pair these with the action taken by the expert at that state. So this is basically trying to learn to recover from our own errors. Okay, so now we take the union of these two data sets, we train a new policy, pi2 on this, hopefully pi2 is a little bit better, and then we repeat this process over and over again. And if you repeat this process long enough, like roughly t log t, where t is the length of the trajectory, you get some nice result that basically says you learn to be like as close to optimal as one would hope. So I'm not going to say too much about the result, but there's some nice theory here. So the biggest issue here is you need a lot of interaction with the expert, right? You need to basically say like, hey, if you did this other thing that you didn't do, what would you do to recover? And so this requires like a huge amount of interaction, and I'm going to try to reduce this amount of interaction later, but this is what we use for the results that I'm going to show you in a second. Okay, so we have these actions, so commit, predict, wait. We have features, which are basically the words we've heard and the confidence of like our final verb predictor and stuff like that. Some language model and translation model scores and so on. Okay, so does this work? So the first question is like, how do I measure whether it works? So we had to invent some sort of evaluation strategy. So there are two things we want. We want a good translation, and we also want it to be speedy. So the way that we're going to do this is we're going to take standard machine translation evaluations, or in this case we're using BLEU, and we're going to measure BLEU at every time point. So what's your BLEU score after the first word? What's your BLEU score after the second word? What's your BLEU score after the third word? And then your total score is going to be the integral of these BLEU scores. So the quicker you can get a good translation out, the higher the area under this curve is going to be, and you're going to get a high score. If you wait forever, you're going to get like 0, 0, 0, 0, 0, and then like good at the end. Okay, so that's our evaluation metric. You should actually not use this evaluation metric. We figured out like 3 months after this paper that there's a pretty easy way to game it. I'm kind of disappointed the system did not learn to game it. So don't use this evaluation metric. That said, I'm going to show you the results. So there are a couple like sort of obvious baselines. So the batch system just waits until the end and then translates the whole thing. So it does very well in terms of quality, but very bad in terms of simultaneity. A monotone system basically translates words or phrases as it goes along. So it's very simultaneous, but not so good in terms of quality. The green bar is humans, so they're very good. And then the purple bar is our learned policy. So we fall somewhere between the sort of obvious baselines and the people. Yeah.
How do you game it?
Ask me at the end. It's a little bit complicated. So it has to do with the fact, it has to do with gaming the brevity penalty. Okay, so the more interesting thing is like what happens as time goes on. So here on the x-axis, we have how much of the sentence have we seen so far. And on the y-axis, we have the integral BLEU score up until that point in time. So red, right? So red doesn't do anything until the end, and then it does pretty well. The interesting thing is comparing the monotone policy and the learned policy. So basically, for most of the sentence, the monotone policy is doing better because it's sort of more aggressive. But then at the end, the learned policy like jumps up because it hasn't committed to as much like rubbish, and it can recover from errors. Right. So the other thing that's going on here is that in German, sort of the biggest reordering issue has to do with the verb at the end of the sentence. And so the fact that we get sort of the biggest gain at the end of the sentence is maybe not super surprising.
So why does the batch perform below the learned at the end of the sentence?
Yeah, because this is not the instantaneous BLEU score. This is the average score up till then. If it were the instantaneous, yeah, red would be up at the top.
So you're suggesting it would be interesting to look at Japanese to or Chinese to English, where you have
more
your prepositional
reordering.
phrases and your yeah.
Yeah. At the time that we did this, we didn't have a good Japanese corpus. Otherwise, that's what we would have done. The other thing is, among the group of people that were working on this, there were like 2 people who knew Japanese and 2 people who knew German. So those were the 2 languages we were working with. But we had more data for German. I mean, we didn't have any data for Japanese at the time.
I mean, something the learned system. What actually are you learning? You're learning the policy. So the difference between learned system and monotone is that monotone case, the policy is predefined.
Yeah, so monotone case, basically monotone can't wait, and it can't predict. So all monotone does is translate as it hears.
I see.
It's not exactly word to word, it's phrase by phrase, because this is a phrase-based MT system under the hood.
But when we talk about learned policy, what are the possible actions?
So this is like wait, predict verb, predict next word, and speak. Yeah, so it's just those 4 actions. Yeah.
There's a trade-off between speed and accuracy, and the metric. How does it is it a parameter to tune it, or?
Yeah, so for this one, there's not, because we're doing sort of this area under the curve thing. So it's sort of implicitly in there that you want to be simultaneous. I think that, so one of the things that we're working on now is look at what human interpreters do and try to reverse engineer what they're actually optimizing for. Because I don't think they're optimizing for this. But I mean, this is a big question, right? So how do you even evaluate, like what is the tolerance that people have for delay versus quality? And it also is going to vary depending on whether the output medium is speech or text displayed on your phone or something. And if it's text displayed on your phone, you might even want to allow it to edit past things. Maybe you don't want it to allow it to do infinite edits and like edits every 5 milliseconds. But you probably do want some edits. So I think this is like a super big question, is like, what is the right thing to optimize for?
It's about the reward function. Have you ever tried, if the reward function is just the boost score, the quality of the sentence, you may learn just wait until the end. It's become bad.
Yeah. So you would like to learn that. You won't learn that because you won't learn that using this algorithm, because this is trying to replicate what the human is doing, and the human is not doing that. So this is a big problem, which I will fix in 2 slides.
So this is running the Bagger algorithm.
Yeah.
So the pi star. So after each step, the human gives a.
So we have a way of reverse engineering what we think the human would have done if they were actually optimizing for this score. So it's a semi-simulated human. Because we didn't have access. I mean, I don't even think you could get an interpreter to do this, right? Say, like, suppose you had said these 5 words, what would you do next? Like, I don't think a human interpreter could actually do that task. The expert decisions are coming from this. Basically, we do a little bit of dynamic programming to figure out what action would the expert take if they were trying to optimize for this. So that actually reminds me, my answer to your question was incorrect. So if you just had blue score, you would hope that you would learn to wait. But we didn't try that.
So this is like a perfect thing for a capture type system, right? You give sort of the sentence that you need to translate, and you give the partial sentence that you have that the system has corrected now, and you ask the human complete the sentence in order to be equivalent to the target sentence.
Yeah, so you could do that. I mean, the tricky thing would be you would want to somehow incorporate the fact that maybe you haven't heard the entire foreign sentence yet. So maybe you only get a prefix of the foreign sentence, and then one of the things that the user would have to do is say, like, I need more or something like that.
Yeah.
But yeah, you could totally do that. If I had 1 million users that I could pester, I would probably try something like that. Okay, so this worked pretty well, but there are a bunch of problems, right? So human interpreters are not optimal. Like they actually make lots of mistakes, and one of the main reasons they make mistakes is because brains are not like perfect. it turns out. One of the like more interesting things I found in like talking to like human interpreters is like I had this view that the reason why they try to minimize delay is to keep the conversation natural. But pretty much every interpreter I've talked to has said that they actually try to maximize delay, except at some point they start forgetting stuff. And the reason that they have to keep up with the speaker is because their short-term memory fails at some point, and if they haven't said it, it's just going to get dropped. So humans are operating under this like short-term memory problem, and the fact that like recall is just hard for people. It's not clear that we actually want to mimic interpreter behavior, right? Like, we'd really, like, I think this is one of these problems where, like, we can actually do better than people, right? Like, probably not today. Actually, like, so we have data from 3 different interpreters, one with, like, 10 years experience, one with 5 years, and one with, like, 1 year. And current systems are, I think, arguably better than the last one. But he's really not very good. Like, if you listen to his interpretation, like, you feel really bad for him because he's kind of just, like, saying words and he's, like, struggling to keep up. So I think we can actually beat that interpreter now. Yeah.
In conference situations, and I perfect the constraints of memory, so great that people are not dealing with familiar topics. But typically they work in pairs, one person doing 10 minutes and the other person taking frantic notes that they pass off to them.
Yeah, that's right. So this is actually something we're working on now, is basically trying to do like interpreter tools. So how to make life better for human interpreters, right? So one of the things that like the note takers will do a lot is they'll write down names or they'll write down numbers. They actually sometimes write down essentially little semantic frames. So they'll write down like verbs and arguments of the verbs and stuff like that. I mean, they don't call them semantic frames, but that's basically what they are. The other thing is, like, when you're working in pairs, like, the whole point is you need to take a break. But if you're, like, frantically scribbling notes, it's, like, not a very good break. So we'd like to do better than people. But if we want to do that, we can't just mimic their behavior. We need some sort of external signal of quality. I'm going to switch to a different algorithm now, but we're going to stick with the driving example. So this is going to be an online algorithm. And so at every point in time, we're going to have some current policy. So we're going to let this policy drive for some number of steps until it reaches some state. We're then going to consider every possible action that could be taken at the state. So in this example, we'll have like left, straight, right. We'll take the first action, and then we'll let the human drive for the rest of time. And at the end, we'll record some sort of external quality signal. So I don't know, think like thumbs up, thumbs down, or, you know, is the person I'm talking to happy, or whatever you can measure. So we get some loss. And then we rewind time, and we go back to this state, and then we choose another action, and we let the expert drive for the rest of time, and then they get some new loss, which we'll say is 0 in this case. And then we rewind back to the state, we take the third action, we let the human drive, and then we get some cost. Okay, so now for every possible action that we could have taken at this state, we have a cost. We're going to create a cost-sensitive classification example where we have the observation available at this state, and then for every possible action we could take, we have some cost associated with that action. And then the job of the classifier is to choose the cost that minimizes, to choose the action that minimizes the corresponding cost.
The cost is the expected cost or real cost?
It's real cost.
Real cost.
Yeah.
How do you collect data?
Oh, this is a big problem. This algorithm you cannot actually run, right? So because you can't rewind time. This requires like an immense amount of interaction with the expert, and it basically can only be done in simulation because you need this ability to basically checkpoint and then go back to some previous state. So I will fix this in 2 slides, but this is just to sort of get the intuition out there. Okay, so the nice thing about this is that we don't need immediate feedback about what's the right thing versus wrong thing to do at every step. And also we get this notion of like some errors are worse than others, right? So like if I can't learn to do the best thing, I'd like to do the second best thing. So on the not bright so bright side, like we have to run this a lot and we have to interact with an expert a lot. And I didn't say, I didn't sort of show the theory, but like this algorithm has some nice theory under the assumption that the human driver is optimal. But like the whole point is the human driver is not optimal. So we need to fix both of these things in order to have like an effective algorithm. So here's like sort of a motivating example for the sort of feedback that we're using. So I didn't know that like iPhones did this, but they have this like voicemail transcription. So I was visiting my mom recently, and she got this transcription voicemail from me that's something like blank, me, IR on PCH. My mom lives in LA. And have fun, be there in about hopefully less than a half hour, funny minutes. I think that was 40 minutes or so. Anyway, see you soon, love you, bye. And then like she has this option to say whether it's useful or not, which is sort of like a thumbs up, thumbs down. Or like if you use Facebook, like Facebook will translate Facebook posts, and then you can often rate them like 1 star to 5 star. So this is some sort of like explicit signal, and this is the thing that we're trying to optimize. Okay, so how are we going to do this without relying on any of the stuff that I didn't want to rely on? It's going to be the same basic flavor. So I'm going to have some sort of learned model, and I'm going to let this run for some number of steps. Okay, so if you want to think about translation, I'm going to let it translate the first 5 words. Then I'm going to stop it, and I'm going to look at the actions I can take at this point in time. And I'm going to pick one of them at random. Okay, maybe not uniformly at random, but I'm going to pick one of them at random somehow. And I'm going to let some other policy, which I'm going to call pi out, drive for the rest of time. Okay, so you should not think about pi out as the expert. You should think about pi out as some existing system that I have that's probably not optimal. So I'm going to run my learned thing up till this point. I'm going to choose some deviation from what it would want to do. So this is some sort of exploration. And then I'm going to use some off-the-shelf system implemented, however, that's probably not very good, drive for the rest of time. And this is going to give me some cost. Okay, so but now I can't rewind time, but I'd still like an estimate of the actions that I didn't take, an estimate of the cost of the actions I didn't take. So I'm going to have some regression system running under the hood that's trying to predict for some counterfactual untaken action what would have been the long-term loss had I taken that action. Okay, so, yeah.
Why can't you rewind time?
If you can do that, we should talk. No, so the reason is because like so the model of interaction that we're assuming is like, so I'm sort of thinking of this Facebook translation model, right? So I see a post on Facebook that's in like German, I click translate, and the system gets to try exactly one translation. Like it doesn't get to say like, which of these 2 translations would you prefer? That would be a reasonable model, so that's often called like dueling bandits. But the version that we're doing is just you get to try one thing, and that's the only thing you get to try. Yeah.
Is that how you could make sure that P out generates a continuation of pi?
Yeah.
Because if you just use some random algorithm, it may never have considered pi, so then it couldn't continue.
Yeah, so you need whatever your current system is to be able to like start at some pre-specified prefix, which for like neural MT is not a problem, which is what we're, yeah.
So is this similar to how AlphaGo is trained?
Yeah, so I mean, this is basic. Let me finish and then let me make a comment about that. So for every action that we didn't take, we have some regression model, which I'm not going to tell you how we train, but there's some way of training it, that's going to predict the cost for the action we didn't take. This is going to give us some cost vector, and then we're going to make the update, just like in the previous case. And then we repeat. Okay, so in a sense, I mean, not in a sense, this is basically a reinforcement learning algorithm, right? So, I mean, it just is a reinforcement learning algorithm. So we've also been playing around with other reinforcement learning algorithms, like more standard things like policy gradient, reinforce, actor critic, stuff like that. In terms of like comparison to existing things, this is most like actor-critic, because this regressor is kind of like the critic who's saying like how good are these different actions. Really, the main difference is like I can prove something about this algorithm for arbitrary function approximation, which is really not true for pretty much all of the off-the-shelf RL algorithms. So I like that. Other people might not care. It seems like in practice, it also does better, but of course it depends on the settings.
So the regression model is trained on label data and then stayed fixed during the
So the regression model is initially trained on labeled data, and then we update it based on the observed costs for the actions that we did take.
So it also has something to do with high out.
Yeah, yeah. So the main thing that matters is the regression model needs to be unbiased. Once it's unbiased, then like theory works out okay.
What's the dependence on the size of the action set?
So the number of samples you'll need will scale linearly in the size of the action set. Hopefully we can do better later, but right now that's what it is.
How often you update the regression model?
Every step.
Every step.
Yeah. Okay, so so how are we going to evaluate this? So we're going to do this in this sort of like running evaluation setting. So you have some existing system and you're trying to improve it over time. Every time you get an example, you make a prediction, you get some loss, and then you update the model. And then you get another example, you make a prediction, you get some loss, you update. And so then the numbers that I'll show you are the average loss over an entire run. So the important thing is you pay for exploration. So the more exploration, if you explore too much, then the user sees a crappy output and the user gets unhappy with you. Okay, so now this is the point where like I feel bad because now I have, this was supposed to be an AI stats paper, but it looks like that's not going to happen based on the reviews. Yeah.
So what was the problem of the reviewers?
So part of the problem was like we didn't do a great job explaining. The bigger problem was that there wasn't really much new theory in the paper, and we basically got theory reviewers, and there was like a mismatch in expectations, I think. So we're working, so I don't, okay, so the mea culpa is I don't have MT experiments to show you right now, so we have a neural MT system running. Hopefully there will be a paper submitted to ACL in like a week, like fingers crossed. But for now, I'm going to show you results on like more basic NLP tasks like dependency parsing and stuff like that, because those were faster experiments to run. Okay, so we have a couple tasks, which, you know, whatever, they're kind of boring, but, you know, it is what it is. So we have some reference, which is the initial system that we're trying to improve on. So the setting here is we train the initial system in a supervised way on a very, very small amount of data, and then we try to improve it over time through interaction. So it gets some like kind of crummy accuracy for part-of-speech tagging, dependency parsing, and syntactic chunking. So then we had this paper in 2015 at ICML, where we proved a sort of nice theorem about this like bandit feedback setting. And then after, so that was basically a theory paper. And then we decided to implement the algorithm and run it. And it doesn't work at all. So you run it on part of speech tagging and accuracy drops from 47% to 2%. Random guessing for part of speech tagging is like 12%. So this is really, really bad. So the main thing that was missing here was good estimates for the cost of actions that were untaken. So the way that this algorithm forms the cost vector is you have the action that you took, and then you have every other action. So the cost of every other action is set to 0, and the cost of the action you took is set to the observed cost times the number of actions. And in theory, this is the right thing to do because in expectation over a random choice of action, this cost vector works out to the correct thing. But in practice, the variance is just so large, and you're actually, like, if you manage to anyway, it doesn't work, right? So it makes things really, really bad. So if you switch from the estimate that I just described to the counterfactual estimate that was in the slide, it actually works. So the accuracy goes up for basically everything. Definitely not to the point of like state of the art had you had supervised data. But here you're basically getting one feedback bit per example, not per word or something. So the amount of feedback is substantially lower. So we did a simple epsilon greedy exploration strategy. You can try other exploration strategies. So we also tried Boltzmann exploration and Thompson sampling. So these improve things like somewhat substantially for part of speech tagging, like 3%, and then like not so interestingly for the other tasks. This was kind of disappointing to me. Like I was hoping that doing better exploration would help. So we tried an experiment where we did what I'll call optimal exploration. So because this is simulated on like on labeled data, every time the model chooses to explore, we could simply have it choose the optimal action to explore to. If you do that, you basically get accuracies that are on par with fully supervised learning, which basically says if you could do better exploration, you could do awesome. But right now, the exploration we're using is not good enough. So I don't know how to fix this, but if you have good ideas for doing exploration, please tell me, and then we'll like solve all the world's problems.
What's the upper bound for this?
So it's like, so in the fully supervised setting, it's like 96, using the feature set and stuff like that we have, it's like 96, 92, and I don't remember what that number is. It's mid-90s somewhere. Okay, so let me, so before I think I'm going to skip the question answering part. If you were hoping to hear about like deep Q learning, then you can ask me later about deep Q learning. But let me sort of stop here and see if there are any questions, and then I want to say a word about implicit feedback, and then we'll sort of wrap up. No, okay, so yeah, so we do question answering too. There's a question, there's a neural network, there are some numbers, there's a better neural network, there are some better numbers. So there are lots of people who contributed to this. So most of the interpretation stuff was Alvin and He, and then most of the bandit stuff was Amr. And most of the stuff I didn't talk about was Mohit and Sudha. Mohit is on the job market this year. You should hire him. He will be on the job market next year. You should hire her too. They're both awesome. Okay, so let me just say like a couple words about like explicit versus implicit feedback, right? So in the stuff that I talked about, I guess I talked exclusively about explicit feedback, where you get some numerical score at the end of the day for how good your translation is or your question answering is in the case of the question answering that I skipped. So I think that this is like useful for the use cases that I sort of described, but I think that like at the end of the day, like we really also need to think seriously about implicit feedback, like the sorry Melanie, say that again. So one of the things that we've been working on recently is sort of this model where at every time step, you get some form of implicit feedback, which is like a sentence. And then once in a while, you also get explicit feedback in the form of like some loss or some reward. And so the obvious thing to do in this case is to learn to predict the explicit feedback given the implicit feedback, and then use that prediction to drive learning. So you can do this kind of works, but I think it's a big open question about whether you can do better than that. And I think there's also sort of this interesting like mixed initiative thing where like maybe you always get implicit feedback, but once in a while you can ask for explicit feedback. And so now there's this interesting balancing act where you want to ask for explicit feedback when it's going to help you learn either to solve the task or to learn how to map implicit feedback to explicit feedback. And so you have to learn to trade these off, and I think that's super interesting to think about. The only work that I've really seen in this direction is this paper, I think it was a year ago, by Mark Rydell at Georgia Tech. So they had this really cute paper where they're trying to use reinforcement learning to learn to play Frogger. And Frogger is apparently like hard to learn. Okay, so some people cheat when they learn to play Frogger, and you get reward for getting further north on the board. But if you just say like, if I get to the top, I get a positive reward, and if I die, I get a negative reward, it's really hard to learn because you basically learn to just stay where you are, because anything you do, you die. So what they did was they hooked the system up to like a microphone where a person can be like, good job, or no, or whatever. And then they did like sentiment analysis on the speech, and then used this to like craft a reward function to like help it learn like this intermediate cost. So this was very, I mean, it's slightly gimmicky. There was not like sort of a nice theoretically justified algorithm, but like I think the idea is like super interesting, and this is something that I'm really excited about. And then the last thing, so I mentioned this at the beginning, but I think this is certainly the case for like the interpretation stuff, but I think it's also the case for a lot of other things. So we have this sort of interesting setting where we have human batch translations, which are like good in one way and bad in another. And then we also have a data set of human interpretations, which are sort of simultaneous they're good from like a simultaneity perspective, but they're bad from like a fluency adequacy perspective, right? And so the natural question is like, how do I learn something that's like the best of both worlds rather than like the worst of both worlds? So we've done some stuff by doing like data munging. So can I rewrite the batch translated stuff to be more simultaneous? And this seems to help, but I think there's probably like, there's a more general question here that I think would be interesting to answer. So I'll stop and take last questions. Yeah.
Maybe naive, but is there room for just combining different experts that have been trained with different, for example, with different exploration strategies, and just like, the simple classifier ensembles where, as long as the classifiers make different types of errors, you can actually combine them and get a better combination result?
Yeah, I suspect so. I mean, the danger is always like, in the model that we've assumed, which is not necessarily the only model you can imagine, but in the model we've assumed, right, you pay for exploration. And so if you spend too much of your time doing crappy translations, you're going to lose users or whatever. So I think that's sort of the danger there. There's a lot of places where we made life harder on ourselves than maybe would be like natural in a real world setting, right? So in all the experiments that I showed, you get to see every example precisely once, which means you get to try only one translation per sentence, which is maybe not totally reasonable, right? Like if I have like Facebook or whatever and someone posts something in German, there's a pretty good chance that multiple people are gonna ask for a translation into English. And so then you can actually try a couple of different versions, and like, yeah, you have the issue that people rate things differently and stuff like that, and there's gonna be variance across users, but you also get much more signal because you can try to actually evaluate these counterfactuals. So, this is one of these things where it's like, it's not quite clear what the right interaction model is. And if you had more opportunity to try more than once on a single example, I think something like this could be pretty effective, but we haven't tried it.
Did you ever use any simulated users in your experiment data?
Yeah, so not in what I showed, but for the neural MT stuff that I did not show, we tried a couple of things. So the first thing we did was the loss you get is exactly blue score. And shocking, you do better on blue score when you optimize that. So then we decided to make it a little bit harder. So we said, okay, we'll take the blue score and then we'll bin it to like 1 star to 5 star. That basically didn't make a difference. I mean, you can still learn to optimize blue score quite well that way. Then we tried adding noise. That obviously makes it harder. You learn more slowly. But then the thing that we're doing now that I think is kind of fun is, so Yvette Graham collected this data where they have about like 100,000 MT system outputs that have been rated by people. And there are a couple hundred raters that have rated over 1,000 sentences. So what we tried to do was learn like a personalized model for each of the raters, like how would Lucy rate this translation versus how would Bill rate this translation versus whatever. And so the input to that is we run a bunch of like MT evaluation metrics, we run some language model scores, and we get a bunch of features. And then we learn, like, I don't know, maybe Lucy cares more about fluency and Bill cares more about adequacy or whatever. Maybe some people are nicer than others. And so now you have to adjust the model, right? But this now looks a lot like,
Sorry, I just raised my hand.
oh, sorry.
No, because you were comparing me and Bill, sorry.
Oh. So but like collaborative filtering people have like dealt with these problems, right? So, I mean, not to the point that they're totally solved, but you know, you need to have like user-specific biases and stuff like that so that you can have, so you know that different people are harsher than others and so on. So that obviously makes the learning harder, but it seems like you can still learn, right? So there's always this problem with like simulated users that maybe it's exploiting some weird bug in the simulation, but I hope that that's not what's going on.
Sorry, a little confused with the last discussion. So by using the human ratings associated with the translated sentences, you're hoping to improve on, get better translations than just training on references?
No, we won't be able to do, I mean, that's not gonna happen. So what we're trying, I mean, basically what I wanna do is I wanna simulate the case where I'm actually getting user feedback on the system. So we basically have 100 simulated users learned off of Yvette's data. And then for every sentence we translate, we pick one of these users uniformly at random to be the user who's evaluating the sentence. And then we predict what their rating would have been had they seen the sentence. And then we use that as the feedback.
So this is to simulate the situation where you don't have parallel data.
Yeah, that's right.
So when you have parallel data, does user feedback help at all?
Almost certainly not.
What about in the...
Well, so modulo the fact that maybe human evaluation is going to disagree with blue score or something like that. But we don't know how to measure that.
So one of the things with, so two questions there. One is like in your simultaneous interpretation situation, do you actually need human input or can you use the references to be the simulated sort of feedback for the simultaneous interpretation?
Yeah, so if we had a good evaluation metric, we could use that as the feedback. Right, so I guess someone asked about this earlier, but right, the problem is like we have no idea what the right evaluation metric is for simultaneous interpretation, right? So what we've done, I mean, not for these results, but what we've done in other stuff is basically some like inverse reinforcement learning where we try to reverse engineer what does the human interpreter seem to be optimizing for, and then try to optimize for that. But then there's the problem that the human isn't optimal, and so it's not totally clear that that's the right thing to do. That's another fun question. So I mentioned we have 3 different interpreters of varying quality. So we don't have an optimal interpreter, but we have like an interpreter gradient. And so maybe you can learn something that they're heading towards. So the other setting we've looked at this is I had this high school student come last summer or 2, and they worked on building a neural network for playing Scrabble. So we have like 50,000 Scrabble game recordings by people of varying quality at playing Scrabble, right? And none of them is optimal, but maybe you can actually learn something that's better than any of them by using the sort of gradient of people's scores. So I don't know if this works. We're trying it. And 3 is probably not enough. But
Because with neural translation, BlueScore is getting more problematic, right? Because as you get closer to perfect, the fact that you only have one reference starts to matter a lot.
Yep. There's another big issue, which is neural MT produces fluent but wrong translations very frequently, and so someone might say 5 stars even if it doesn't have anything to do with the source sentence. And I don't know what to do about that.
But as you were mentioning, that lag maybe it doesn't impact the ability to have a conversation quite as much as we think it does, and maybe it's because of this short-term memory. So are there any studies where you just kind of see, okay, what are people's tolerance for delay? And where's that sweet spot that maybe isn't a function of the person's short-term memory, but for the conversation, which is what you're trying to actually do?
So I don't know of any studies. I mean, the best I can talk about is there's lots of work in interpretation studies looking at, I mean, so for instance, like we have in our communications school at Maryland, we have a training program for interpreters, and they get grades, right? So you might ask, like, how do they grade the interpreter? There's also, for instance, like if you want to be a court interpreter, you have to take an exam. I would love to get this data. So in like the state of California, they have a fixed recording that they play for you and you interpret, and then graders mark up. They have like a list of like 1,000 different types of error categories, and they mark up, and then you get a grade, and if you get a high enough score, you get to be a court interpreter. The problem is as soon as it's graded, they throw out the data for like whatever privacy reasons or something like that, which, so frustrating. Like I would love that data. So there's lots of stuff that they look at. I mean, a lot of it is stuff that we're never gonna care about. So things like poise and like, are you dressed well and stuff like that. But there's relatively little focus in the evaluation on the ear-voice span. And I think this is basically because of the human constraints that if you let it grow too big, you're gonna make other errors, like dropping material. And so most of the evaluation in terms of content is really about, did you preserve the meaning? So we were hoping that there would be, they would say like, oh, your grade on this exam is, 0.5 times your score plus 0.2 times the amount of time it took plus whatever. But I think that these methods just don't generalize to systems that are not memory constrained. Because you would do perfectly on this if you just waited until the end of the entire 10-minute speech and then translated the whole thing. You would pass this exam according to their current evaluation. So yeah, I was hoping there was more we could use there. So we are using this I mentioned earlier that we're doing this stuff where we're trying to do interpreter tools to help human interpreters do a better job. And there we can look at things like, does it actually help them according to the standard interpretation grading? But for actually evaluating systems, it's much less clear. And it's also going to be context dependent, right? Like if I'm talking to my doctor, I'll tolerate much more delay than if I'm talking to a friend or something like that. But yeah, it would be a cool study to do. Like, what is people's tolerance? You would probably need to do some sort of Wizard of Oz experiment. It's kind of hard because you would want, yeah, it would be hard to do.
In some sense, it matters what the setting is, right? If you're speaking and I'm getting the translation of what you said 10 words later, but I can't either see you or hear you in the original. Maybe I don't know that it's 10 words later, so I have no idea. If I can see your mouth moving, then maybe it's bothersome, or maybe I just learn not to look at you, because presumably even you one word off, like look at your mouth, is going to be like pretty disturbing. But if I'm sort of hearing you speak in the background, maybe that's even more confusing.
Yeah, I mean, I think, so I've kind of come to the belief that really the use case for the simultaneous stuff is dialogue, right? So like Alex Weibel has this like classroom interpretation stuff, I think in Heidelberg, where they'll interpret like lectures from German into English. And there it's not to speech, it's to text that appears like on a web page or something. Yeah, like that, but bigger probably. But I feel like if there's like a 1-sentence delay, it's not that big of a deal. It could be a little bit annoying if like the person has gone on to the next slide in their talk. So you see this in like closed captions too. But like, okay, so just have the slides delayed 10 seconds on my laptop. Like, I mean, I feel like there are other like solutions to this problem that, yeah, and like TED Talks, like, I mean, who cares? Just delay the video 20 seconds or something. And so I really feel like it's the interaction case that matters. Yeah.
I mean, here it's running about 4 or 5 words behind, and it doesn't seem to matter. I've been reading it.
Because you're bored.
I have a professional interest in the accuracy of the delay.
It's
also distracting.
I mean, the other thing is that, you know, the ASR is going to run a couple words behind. If you're doing speech synthesis, that's going to run a couple words behind because it has to get prosody right. And so you're already like maybe 5 words behind. I mean, you really want to do these things jointly, right? Like maybe when the speech recognition system is confident, then you don't want to let it delay for 2 words, but when it's uncertain, you want to allow it to wait. So I don't know, you'd really want to integrate these things, but I don't know anything about speech, so don't make me do speech.
Along those lines, is sign language like just sort of a literal translation word by word, or does it also have some reordering aspects?
No, there's also lots of reordering. So, so like American Sign Language, I believe is verb initial. Does anyone know for sure?
Not always.
Not always. But I think it's definitely not like just sort of a transcript.
So have you considered that as another, I mean, it seems like you could get a ton of data there.
Yeah, so we've thought about this a lot. So there's 2 questions, right? So one is, what direction are you going? Are you going into sign language, or are you going out of sign language? The other, so we were mostly thinking about going into, but then it's not totally obvious to me whether you want that or whether you just want text displayed on a screen, right? So do I want a little avatar on my phone that's speaking sign language, or do I want a transcript written down?
Right.
And it's not totally clear. So, and then if you're trying to do the other way, so like sign language to English, like all of a sudden now we need all this like computer vision, and that's like complicated. I mean, people have worked on this. Like there is a bunch of work in both directions, more into sign language than out of sign language. You know, and then I guess to be perfectly frank, like, you know, like I said, we did German and Japanese because we know German and Japanese. None of us know ASL, which is maybe not the best reason, but it would certainly be very interesting to look at. So far, we haven't. Okay, sounds good. Thanks a lot.